So today is about areas of regular polygons. Okay, so the learning goal. First of all, these diagrams are here to remind you what the names of the different polygons are. So as I'm discussing this, you might as well just take a look at the names here of these polygons. So in the previous lesson, you developed a method to calculate the measures of interior and exterior angles. Today, what we're going to do is use what we know about the angles and like how to break down the polygon into triangles to determine the area of a regular polygon. So in the past, you have done area problems involving finding the area of a triangle, finding the area of a square you've done before. But then what do we do when there's lots more sides than that? Like, how do we find the area of these things? And so we're going to come up with a strategy today to address that. So our essential question is, how do you calculate the area of a regular polygon? And of course, it's okay to not know at this point, but go ahead and jot down your initial thoughts. All right, so the first one we're going to find is the area of this square. So normally, squares are easy to find the area of if we know the length of the side. So then we just go like base times height, like a rectangle. Find the length of the side, times it by the other length, and we're good. The problem here is that the given length that we know from this diagram, the thing that they tell us in the diagram is not the length of the side, it's this weird length. So there's more than one approach to figuring out the area of this square. One way would be to try to go the traditional route and figure out the length of the side and then use the area of the rectangle formula. And you could absolutely do that. Like you could use this special right triangle, recognize that this length 6 is one of the legs of an isosceles right triangle. And so then that would make this 6, that would make this 6. So the hypotenuse of that would be 6 root 2, which would be the side of the square. And you could totally go that route. But I'm going to show you a different route that might be a little bit more useful when we get into polygons that have more than 4 sides. So I'm going to show you a new sort of approach to finding the area of the square. So remember that if you have two base angles congruent in a triangle, that it's isosceles. So that means that this length right here is the same as this length right here. So not only is that one length they gave us 6, but this right here is also 6. Okay, so we have this triangle in here, this right triangle with two sides that are 6. Now, what if we focus our attention in on this triangle? What if instead of finding the length of the side of the square in order to use the rectangle formula, we found the area of one triangle and then multiplied by 4, because we have 4 of the same little triangle in here. So this is what we're going to do. So what I'm going to do is I'm actually going to redraw that triangle, and I'm going to orient it in a way that might be a little bit more useful for us. So I'm going to take this triangle that I highlighted in yellow, and I'm going to redraw it up here. So that the right angle is there instead. So I'm going to like redraw it like this. So here's my right angle now. And what I know is that this side is 6. And I know that this side is 6. Okay. And we do have 45-degree angles, but they aren't actually that useful to us in this situation. So here is how we can find the area of this. Remember that in the area of a triangle, or in a triangle, the base of the triangle and the height of the triangle are always perpendicular to each other. So if we have a triangle that happens to have a right angle in it already, then these two sides are the base and the height of the triangle, even if they didn't look like it in the diagram originally. You can rotate a triangle and not mess with its area. It stays rigidly the same. So what I'm going to do now is I am going to recognize that the base of this triangle is 6 units long, and that the height of this triangle is 6 units long. And once I know the base and the height, all that's left to do to find the area of that triangle is to use the area of the triangle formula. So I am going to do that. So right here, I'm going to find the area of the triangle. So area of triangle. And the area of the triangle is with the formula. So I'm going to go, area equals 1/2. So I'm going to write 0.5 just because I'm typing, but you can write the fraction if you're writing by hand. 1/2 times the base times the height. And then calculate it out. So this is A equals 0.5 times 6 is 3 times 6 is 18. So we have 18 square units for the triangle. But we're not done, because remember, the whole problem was not asking us for the area of the triangle, it was asking us the area of the square. So now we have to go back to the original diagram and go, okay, now that I know that the area of this yellow triangle is 18, how can I use that to find the area of the whole thing? And I recognize, oh, wait, I have 4 identical triangles here. If that's a right angle, that's a right angle, and that's a right angle, and that's a right angle. So we have 4 right angles. These are all isosceles triangles. This would be 18. This would be 18. And so would this. So we would have 4 identical triangles that each have an area of 18. So the final conclusion here is that the area of the square equals 4 times 18, because we have 4 triangles with an area of 18. So that means that the total area of the square is 72 square units. Boom. There is our final answer. So just to recap, this isn't the most intuitive way to find the area of a square. Like ideally we want to get the length times the width if we have a square. That's like maybe the most straightforward for a square. But this method of finding the area of one of these triangles and then multiplying it by 4, how many triangles we have, ends up being a really useful technique for polygons that have many more sides than a square. Okay, so now we're going to look at a polygon that is a little more complicated than a square. So this is a regular hexagon, meaning it's a 6-sided figure and all of the outer lengths are equal. So this length that they give us is 8. So is this. This is 8, this is 8, this is 8, this is 8, this is 8. All right, so we're going to approach this in a similar way. The goal is find the area of the triangle and then times by the number of triangles that we have. Well, right now I only see one triangle, but what we can do is kind of imagine how there are actually several other triangles in here. You see? So if I connected all these lines up, now I have 1, 2, 3, 4, 5, 6 identical triangles. What I'm going to do is first concentrate on how to find the area of the one triangle, and then I'll times by 6 at the end. So in the previous problem, we found the one triangle and multiplied by 4 because we had 4 triangles in a square. Now we have 6 triangles in a hexagon. So I'm going to focus in my attention on this triangle right here. This is our key triangle. Once I have the area of this yellow triangle, then I multiply by 6 at the end, and I'll have the area of the whole thing. Okay. but now we're in a situation. That 60, 60, 60 equilateral triangle, it's not a right triangle, which means we don't know the height. So what I need to do is a little extra legwork on this one. So what I'm going to do is I am going to draw in a height. And the height has to be perpendicular to the base. And because this is equilateral, that line perfectly cuts the top angle, the 60-degree angle, in half. And it cuts the bottom side, which is 8 units long, in half. So what I'm going to do to find the height in order to be able to use my triangle formula and get the area of the yellow triangle is I am going to actually look closely at this half of the yellow triangle, which is a little right triangle. So up here off to the side, I'm going to redraw an enlarged version of that red outlined triangle I just identified. Okay, so this triangle, this left-hand side, this half of the yellow triangle is redrawn up here. And I'm going to start putting in information that I know. So I know, because it's in my original problem, that this little angle right here at the bottom is 60 degrees. So I know that. Okay. And then I know, because I just sliced the top angle in half, that instead of 60, this top angle is half of 60, which is 30. I also know that the bottom edge of this triangle, which is half of 8, has to be 4. What I'm trying to find is the height. So I need to find the height. The only way I can get the area of this yellow triangle is if I have the height, like 1/2 8 times the height. Like the base is 8, I don't know the height. So we have to find the height. So we're going to use this right triangle, in the half right triangle, to help us find the height, and then go back and find the area of the yellow triangle. All right, so now there's a couple ways to approach this. One way is we could use trigonometry. I could straight up go like opposite over adjacent. So tangent of 60 equals h over 4. I could do that. I could use trig to find the missing height. I could also recognize that this is a special right triangle that has these special side relationships that we learned in a earlier section. So remember this 30, 60, 90 special right triangle. So I'm going to use this because it's probably the most efficient. So notice how in this 30, 60 right triangle, the smallest length, the shortest leg, is 4. In the toolkit, the special right triangle, the shortest leg is x. So if x is 4, then the side perpendicular to it is 4 times √3. So using this diagram right here as sort of a guide, I'm just matching up my sides. So if this length here is 4, then our x is 4. Those correspond, which means this h right here is 4 √3. Those correspond. So this tells me that this h right here, has to be 4 times the square root of 3. Based on this special triangle. Okay. So I just found what I needed. All right, now it's time. Maybe I'll use my straight line tool for that. Now it's time to actually find the area of the yellow triangle. So now I'm going to go back and use h is 4 √3 to find the area of the yellow triangle. So the yellow triangle has 3 equal sides. It's equilateral. The base of the yellow triangle is 8. oops, the base of the yellow triangle is 8. And then the height, right? I'll go ahead and draw in the height. The height of this yellow triangle, or of the equilateral triangle, is now 4√3. So when I find the area of the triangle, I have area, which is equal to 0.5, because I'm using the formula, that's my 1/2, times the base, which is 8, times the height, which is 4, times the square root of 3. And I'm going to totally put the square root symbol in there in just 1 second. Be patient with me. I'm going to up my font here. So this is 4 times the square root, square root of 3. All right, so now I have A equals, oops, 0.5 times 8 is 4, and 4 times 4√3 is 16 times the square root of 3. That was sloppy. Here we go. 16√3. That's the area of our triangle, of the yellow triangle. So I'm not done yet. I found the area of the yellow triangle, but now I have to find the area of the whole hexagon. So we have to go a step further and be like, which means the area of the hexagon is equal to 6 of the yellow triangles. 6 times 16√3. All right, well, 6 times 16, that's 96. So in the end, and I'll just write this freehand, 96√3, and this is square units. 96√3 square units. All right, so this slide is all about sort of like the key parts of the regular polygons and how to find their area. So in the first sentence, it says, if a polygon is regular, that means all sides and angles are congruent. There's a little note on this side. With n sides, so like an n-gon, we don't like the number of sides is n. It can be subdivided into n congruent isosceles triangles. So it can be like broken down into these identical triangles. So notice how in this diagram, this is a 5-sided figure, a pentagon. And when we draw in these triangles that go from a vertex to a center, they're 5 triangles. Pentagon has 5 triangles, hexagon has 6 triangles, heptagon has 7 triangles, and octagon has 8 triangles, and so on. The number of sides and the number of triangles is the same. Okay. Now, one way to calculate the area of a regular polygon like this is to multiply the area of one of the isosceles triangles by n, the number of triangles, or the number of sides. So in purple here, this is essentially like our formula. We have the area of the regular polygon is equal to the area of one triangle times the number of triangles, times n. The hardest part about this is figuring out the area of one triangle. But the goal here is like that we're trying to just find the area of a triangle. And then the last step, times by n, is a quick, like, final thing to do. All right, so essentially finding the area of a regular polygon is basically finding the area of a triangle. and then times by how many triangles. All right, so again, remember I was saying that there's a lot of different parts that come into how to find the area of the triangle. So if you have a base and a height already for you, then this is really straightforward. You just use the triangle formula and go from there. But sometimes we don't. So sometimes we need to get a little creative about how we find the missing base or the missing height of the triangle in order to calculate the area of the triangle. Remember in the previous example, we used the special 30, 60, 90 triangle side relationships to help us to find the height. That's one way to do it. Another way would sometimes we can use Pythagorean theorem to find a missing height. And then another way would be to use trigonometry. And for trigonometry, we always need at least one of the acute angles in a right triangle to help us find the missing side. So this is where this next part of this slide comes in. So in a regular polygon or circle, the angle formed by two radii, that's like a radius, and that's a radius, more than one radius is radii. With the vertex at the center is the central angle. So this little like arrow is pointing at this angle that's formed at the center of the polygon. That's the central angle. And to calculate the area of an isosceles triangle, you can first figure out the measure of the central angle and then divide by, so you can basically like find the measure of this angle. And then once you know that, that will help you to find the angle at the top of this little right triangle that I just created, which this little line bisects. So I just drew in the height at a right angle. That height, that little line segment I just drew in pink, cuts the central angle in half. So there's a couple things happening here. So first of all, this 360 degrees thing, it's on purpose. When we rotate a full circle around, that's 360 degrees. A full circle is a 360-degree rotation. But if we only want a partial rotation that just gives us the central angle, what we just need to recognize is that every one of these central angles in this diagram would be equal to each other. So all we have to do is take 360 and divide by the number of angles that we have or the number of triangles that we have. And that will give us one of them because they'll all be identical. So this expression, 360 over n, gives us the full central angle. And then we would just divide that in half to get half of it so that we have part of that little right triangle I just created with the height. And we're going to see this in action in an example. So don't worry. Here we go. Okay, so this example is already worked out for us, and we're going to do one all together that's similar to this, but I want you to see it sort of like have like a nice typed up example for yourself to refer back to that's organized, okay? So this question is asking us to find the area of a regular decagon, which has 10 sides, and each side length is 8. Okay, so remember in all of those, in those two other area problems we didn't really pay attention to the full shape. We just looked at the triangle. And then at the very end, we multiplied by how many triangles we had. So this is basically like, we're just ignoring that we have a decagon, which has 10 sides, and we're just looking at its triangle. And at the very end, we will multiply the triangle's area by 10 because there's 10 of them. So this triangle happens to be like one of 10 triangles in a decagon. Can you see, like, could you imagine this being built out like all the way around? There's 10 of these triangles. So this is just one of them. All right, so we're just focusing in on the one triangle. And then at the end, we'll times by 10. Okay, so our very first step, find the central angle. So remember, the central angle is the angle at the top of this isosceles triangle. So it's both of these two top little angles together. It's the full top angle. So we take 360 degrees and divide by 10 because we have a decagon. So this is where the 10 comes from. We have a decagon, so we divide by 10. So that gets us this whole angle right here that I just highlighted in green, the whole thing. The second step is to get half of that. And the reason we want half of that, we divide the central angle by 2, is because we really want to deal with the right triangle that's shaded. So we do 36 degrees divided by 2, and that's 18 degrees, and that's right here. So that's the angle of just the shaded half. So now what I'm actually going to do is I'm going to redraw the shaded triangle down here so that we can refer specifically to that and it won't be like overlapping. So I'm going to just look at the right triangle right here, and then we can kind of come back to the isosceles triangle in the end. So here's our right triangle. Wow, my drawings are really, really messy. Okay, so here we go. Here's our right triangle, the shaded one, and I'm going to add the things I know to it. So I know now that this upper angle right here is 18 degrees, okay? I don't know the height, h. I also know that because this whole bottom of this triangle here is 8, that the length of the gray shaded triangle on the bottom is half of that, which is 4. My cat is coming in to help out again. She's really helpful. All right, so basically we have a base of this triangle is 4, and then a height we don't know. So now we don't have a special right triangle anymore. This isn't 30, 60, 90. It's not 45, 45, 90. We're kind of stuck. We have to use trig. We're stuck. We have to use trigonometry for this. Yeah, I know. It's really frustrating me. I'm sorry about that. Okay. My cat is not down with trig. All right, so take a look. We have this angle here. It's 18. That's our theta. And then I'm going to label my sides. So remember, this is hypotenuse, opposite, adjacent. And then when we think about SOHCAHTOA, you can see that in this situation, we're not going to use the hypotenuse. We want to find the adjacent. We know the opposite, so we're going to use tangent. So this is where this equation comes from. So tangent of 18 degrees is the opposite side, which is 4, over the adjacent side, which is h. And that's where that comes from. Okay. So now that calculation, this is a proportion that was solved. So you can just like put this, you can put this tangent 18 over 1 and punch tangent 18 in your calculator, cross multiply. So tangent 18 times h equals 4, and solve for h. And so what we get is that the height is now 12.311. So now we have the height of our original triangle, which is 12.311. Because they're the same height, right? The height of this triangle that we use for trig is the same height as that larger triangle above. So now we have a height that is 12.311. We already knew that the base of the original figure was 8. So those are the numbers that get plugged into the area formula for the triangle. So we're using those two numbers in here. And we find that the area of the triangle is 49.242. And then the very last step, remember, is to remind ourselves, oh yeah, we're trying to get the area of a decagon. So we have to times by 10 because it's a decagon. And so then our final answer is 492.42. Woo! Okay. So again, just to recap, the goal, the last two steps are the steps that will always happen for every problem we do like this. We will find the area of one triangle and times by the number of triangles we have. Step 4 and step 5. How we get the information to be able to do step 4 is the tricky part. Okay, so sometimes we use trig like this. Sometimes we use special right triangles. Sometimes we use Pythagorean theorem. Sometimes the information is there for us and we can just jump to step 4. So we just have to like see what we have and work with it and get creative sometimes to find the base and the height. All right, so for this question, we're going to find the area of these two polygons. So in part A, in both of these, we'll have to do this, but the first thing you want to do is be able to picture the triangles that we're working with here. We need to be able to picture those triangles. So I'm going to go ahead and draw in the triangle that goes from a vertex of one of the polygon to the center. And then I'm going to go to the next one down and draw in this one as well. I need to find the area of this triangle. And once I have that area, I can multiply by the number of triangles that can be built inside here, the number of identical triangles to this. And if we count all the way around, you can actually see we have this one triangle, then, so there's 1, 2, 3, 4, 5, 6, 7 triangles. So in the end, we're going to find the area of the triangle I outlined in blue, and then we'll times by 7. All right, now, those marks I just put in there are marks I'm allowed to put in because we know that they are regular polygons. These are regular polygons, which means all their sides are equal. So if that side over here is 13.9, so is this one over here. So I'm going to go ahead and write 13.9 right here. This side just happens to be the exact same length as every other side around the edge of this thing. And here's what's awesome. That means we have everything we need to find the area of this triangle already. To find the area of this triangle, we need a base, which is 13.9, and a height that's perpendicular to it, which is 14.4. We have everything we need to find the area of this triangle. So we're just going to go ahead and do it. I'm going to jump to like step 4, basically, and go the area of the triangle is equal to 1/2, or 0.5, times the base, 13.9, times the height, 14.4. Okay. So that equals a number, which I will find in just a moment. 100.08 square units. So these problems are actually kind of awesome when you have like all that stuff, information is there for you. You're like, all right, that's no big deal. I found the area of the triangle. Now all I need to do is find the area of the whole figure. And this figure has 1, 2, 3, 4, 5, 6, 7 sides. So it's a heptagon. So the area of the heptagon is equal to 7 of the triangles. So 7 times 100.08. So let's just times that by 7, and we get 700.56. And we're done. So when the triangle has the information already there for us, it's not that hard of a problem. Like we can go straight forward through. We just like use the triangle, identify the base, identify the height, plug them into the triangle formula, times by however many we have. Okay. Now, part B is a little bit different. So notice in part B how we also have a height. So let's actually draw in our triangles over here again. So we need a triangle. So I'm going to go from one vertex to the center, and then from the next vertex to the center. All right, so there's our triangle. And we actually know the height of this triangle. It's 5. Just like we knew the height on the part A was 14.4, we know the height here is 5. So we have the height of that triangle. What we don't know is the base. So we need to do a little extra work to find the base of that triangle so that we can find the area of the triangle so that we can times by however many triangles we have. So what I'm going to do now is I am going to redraw half of this triangle, like the left-hand side of this triangle, larger so that I can like really get the details visible. So there's our little right triangle. It's like half of that blue triangle in the diagram. And the details I know are that this is 5. And that's basically the only thing I know. Okay. So what I need to do is find this length along the bottom. Like this is really the goal right now. Like what is this length right here? What is this unknown length? So I'm going to call it X. If I don't know something, I get to pick a variable. So I'm just going to call it X. It's not the base that I care about. The base that I care about will be on the original diagram. It's just the bottom of this half triangle, right? So now what I need is some sort of method for finding that length. And unfortunately, I don't know the hypotenuse of this right triangle, so I can't use Pythagorean theorem. I think I need an angle. So what we're going to do is find the central angle. So remember, the central angle is basically 360, which is a whole rotation around, but then we divide it up by how many triangles we have. So just let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 triangles. So that means our central angle will be 360 divided by 10, which is 36 degrees. So this central angle here is 36 degrees. So if we cut 36 degrees in half, we get 18 degrees, and that's the degrees of this angle in our diagram over here. This is a decagon. We dealt with the decagon with the example that was all typed up. So this is like the same central angle and same half angle, 18. Now we have enough information to find the length of X using trigonometry. So I'm going to use some trig. Here we go. All right, so in relation to our 18-degree theta, this is hypotenuse, this is adjacent, and this is opposite. And once again, I'm not using hypotenuse, so we're talking in SOHCAHTOA. We're going with tangent because tangent relates the opposite to the adjacent. So I'm going to write myself an equation. All right, here we go. The tangent of 18 degrees is equal to the opposite, which is X, over the adjacent, which is 5. And then I'm going to put this over 1, and we'll do a little cross multiply. So 1 times X is X. And then I'm just going to punch this in tangent 18, get the decimal, tan 18, make sure you're in degree mode. and then I'm going to multiply by 5. So tangent 18 times 5 is 1.62. All right, now I know that x is 1.62. So I'm going to use that 1.62 length to determine the base of the original triangle that we care about. So remember, the triangle we care about is this triangle, this whole thing. This one over here is half of that. So if this length is 1.62, I just have to double it. So just like basically go 1.62 times 2. I'm not going to do that. I'm going to go like times 2. And that will get us our base, which is 3.25 about. So right here will be 3.25. So the base of our yellow triangle is 3.25 because it's twice as big as x. And now we can find the area of the triangle. Yay. All right. So, whoops. Area of triangle is 1/2, so 0.5 times the base, 3.25, times the height, 5, which is 8.125, so that equals 8.125. And then we just have to times by how many we have. And remember, it's a decagon. So the area of the decagon is 10 of those because it has 10 sides. And that would be a total of 81.25 square units. And we're done. Okay, so here's our last problem. So this is some girl, Beth, some lady Beth. She needs to fertilize her flower bed, which is in the shape of a regular pentagon. It's a witchy flower bed. All right. A bag of fertilizer states that it can fertilize up to 150 square feet. So this is something we're going to care about towards the end of the problem. So one bag of fertilizer is up to 150 square feet. She's not sure how many bags of fertilizer she should buy. She knows that each side of her flower bed is 15 feet long. All right, so, and you can see in the diagram, we have the edge is 15 feet long. Using the diagram, calculate the area of the flower bed and tell Beth how many bags of fertilizer to buy. Explain how you found your answer. Okay, so remember, first thing, we really need to look at our triangle. All right, so I'm going to draw a triangle. So I'm sort of eyeballing where the center is, but hopefully, get it as accurate as you can to where you think the exact middle of this thing is. And there's one triangle. And we know that we eventually will have 5 of these, but we're going to find the area of this one triangle and then times by 5. And that will help us to determine how many bags of fertilizer she should use or she should buy. All right, so we know the base of the triangle. So when we're finding the area of a triangle, we go 1/2 base times height. We know the base. We don't know the height. So I'm going to go ahead and draw in a segment to represent the height. And this will be at a right angle to the base. And this, I'll label it H. Okay, so in order to find the area, we need to do a little extra work to find the height. this is very similar to example B. Or we had the height before, then we had to find the base. Now we have the base, we have to find the height. But we're going to use trig to do it. So the first thing we do is find the central angle. And this will help us to then find half of the central angle, so we can focus in on half of this triangle to find h. All right, so for the central angle, we go 360 and we divide by how many angles we have, which is 5, like 5 sides. And that would get us 72 degrees for our central angle. So our central angle is 72 degrees. All right. And what that represents is this full angle up here, 72 degrees. Okay, that's the full angle right there. So what we're going to do now is focus in on just half of that triangle. So I'm going to go ahead and redraw just half of the triangle over here. And this is our little right angle here. Sorry, so messy. And then we're trying to find H. Remember, this is like the side we don't know. So we're trying to find H. We know that it's half, and we know the full length of the bottom of this triangle in the original diagram is 15, which means that this little edge here would have to be 7.5, which is half of, oh my goodness, what just happened? 7.5, which is half of 15. So that bottom length of this half triangle is 7.5. And then we know that the central angle on the original triangle is 72 degrees. So if we cut 72 degrees in half, we get 36 degrees. So that's the degrees inside this angle in our diagram here. So this would be 36 degrees up in there, which is half of 72. So like 72 divided by 2. That's where this comes from, okay? All right, so now I'm going to use trig to find h. And once I have h, I go back to my original diagram and find the area of that triangle. And because remember, really the goal is eventually to find the area of this whole thing so that we can then times by 5 and have the area of the whole diagram. So let's use trig. All right, so our angle that we care about is 36. That's our theta, which makes this hypotenuse, opposite, adjacent. And look at this, it's tangent, once again, opposite, adjacent. So I'm going to set up an equation. Tangent of 36 is equal to opposite over adjacent. And then for those of you who felt maybe a little weird about this calculation before and like not working it out all the way, I'm going to cross multiply. I'm going to multiply tan 36 times h and get the decimal for that while I'm at it. So I'm going to just type in tan 36. So that's 0.7265 times h. And then that's equal to 7.5 times 1. And then I divide out by 0.7265 on both sides to get h by itself. And we get 10.32. Okay, so there's our height. So now we can go back to this original diagram. This is 10.32 for our height. And this now means we can find the area of the triangle. Okay, so the area of the triangle will be 1/2, so 0.5. times the base, which is 15, right? Because we're doing the yellow triangle now, times the height, which is 10.32. And that gives us a total of 77.4. And then we need the area of the pentagon. So we have to multiply this by 5. So the area of the pentagon is 5 of those triangles, 5 of the 77.4 area triangles, because there's 5 of them in there. And that is a total area of 387 square feet. Okay, so let's back to the problem. Beth needs to fertilize her flower bed, and she has 387 square feet she needs to cover. She knows 1 bag of fertilizer gives us 150 square feet of coverage. So 2 bags would give us 300 square feet of coverage. So that's not enough, which means she needs to buy 3 bags of fertilizer. Beth needs 3 bags of fertilizer to cover it. She'll have leftover, but she can't buy partial bags. So this is how many she has to get. And that is the conclusion we make here.